We mentioned previously that the second law of thermodynamics states that the entropy of the universe is increasing. In fact, for a spontaneous change to occur, there must be an overall increase in entropy. You may think then that in order to predict whether a chemical reaction can take place spontaneously, it would just be a case of seeing whether the standard entropy change of reaction is positive or not. Let's explore this idea. Professor Polyakov and his team at the University of Nottingham have put together an excellent set of periodic table videos. In the fluorine video, it shows iron wool reacting spontaneously when it comes into contact with cold fluorine gas.
So this is now going to release the fluorine, and what I've got in this demonstration here is just a scouring pad. Basically, it's a metal scouring pad, iron wool.
It's burnt a hole right through the iron wool. It's extraordinary. The iron looks as if it's rusted, but the rusty colour is actually iron fluoride.
Now let's look at the balanced chemical equation for what we have just seen. We have 2 moles of iron solid reacting with 3 moles of fluorine gas to make 2 moles of iron 3 fluoride. So we have gone from 3 moles of gas on the left-hand side to 0 moles of gas on the right-hand side. Consequently, the entropy change for the reaction is clearly negative. At first, this may seem to contradict what we said earlier, that for a spontaneous change to occur, the entropy must increase. However, the definition of entropy involves the dispersal of energy. When we inspected the chemical equation, we only considered the entropy changes of substances involved in the reaction, and we did not consider the change in entropy of the surroundings. Clearly, in this highly exothermic reaction, energy would have been transferred to the surroundings in the form of heat, which would have caused the molecules in the surroundings to have increased their disorder/entropy by, for example, increasing their vibrations and rotations. If we are going to try to predict whether reactions are feasible, therefore, we must take into consideration the exchange of energy between the system, that is, the reactants and products, and the surroundings, in addition to the changes in entropy of the system. Willard Gibbs, an American scientist and engineer, came up with the idea of free energy, this being the energy that is set free by a process during a spontaneous change. Free energy has the same units as enthalpy, that is, kilojoules per mole, and is calculated from this equation, where delta G is the free energy change. We can see the value for the free energy is made up of 2 terms. One is a contribution from the enthalpy, and one is a term involving entropy and temperature. In order for a process to be spontaneous, the value for free energy change must be negative, which means the process is energetically favourable. In this graph, we have values for delta G shown in green, delta H in red, and T times delta S in blue. We will explore the effects of the magnitudes of delta H and T delta S on delta G. The more negative delta H becomes, the more negative delta G, and so the more exothermic a reaction, the more spontaneous change is favoured. Also, the more positive delta H becomes, the less negative delta G, and the reaction becomes less favoured energetically. The situation with T times delta S is different, however, because we are subtracting this term. As T delta S becomes more positive, delta G becomes more negative, and so spontaneous change is favoured. The more negative T delta S becomes, the less energetically favourable the reaction becomes. In situations where delta H is negative and delta S positive, therefore, delta G is always negative and reactions are feasible. In situations where delta H is positive and delta S is also positive, whether the reaction is feasible or not depends on the temperature. At lower temperatures, the second term involving delta S would be smaller in magnitude than the first term, and then delta G would be positive and the reaction would not be feasible. However, increasing the temperature would make the second term in the equation bigger, since we are multiplying the contribution from the entropy by the temperature. Eventually, the magnitude of the second term will become larger than the enthalpy term, and delta G will become negative. The reaction will therefore only become feasible at higher temperatures. When delta H is positive and delta S negative, the reaction is not feasible, since it does not matter what we do to the temperature to change the size of the second term, we will never be able to make delta G negative. When delta H is negative and delta S negative, at lower temperatures, the second term will be smaller in magnitude than the enthalpy term, and so delta G will be negative and the reaction will be feasible. However, if we increase the temperature, this will make the second term larger in magnitude until it becomes greater than the delta H term, and delta G becomes positive and the reaction is not feasible. The reaction will only be feasible, therefore, at lower temperatures. When performing calculations using the Gibbs equation, you must remember to ensure that the entropy change term has the same units as the enthalpy change term. Entropy changes are often expressed as joules per Kelvin per mole, whereas enthalpy changes are often expressed as kilojoules per mole. Therefore, we often need to change joules per Kelvin per mole to kilojoules per Kelvin per mole, and to do this we divide by 1000. Also, the temperature needs to be in Kelvin. To change degrees Celsius into Kelvin, we add 273. And to change Kelvin into degrees Celsius, we subtract 273. For an endothermic reaction with a positive entropy change, you may be asked what is the minimum temperature the reaction becomes feasible. To do this, you assign a value of 0 to delta G, as you want the temperature delta G just becomes negative. You can then subtract delta H from both sides and cancel, and multiply both sides by -1. Then divide both sides by delta S and cancel. The temperature the reaction becomes spontaneous is the enthalpy change divided by the entropy change. It must be stressed that using the Gibbs expression to determine whether a chemical process is feasible does have its limitations. Some reactions do yield a negative value for delta G, but do not occur spontaneously because the activation energy is too high, and the reaction requires an input of energy to first get the reaction going. Also, some processes may have negative values for delta G, but the reactions proceed at far too slow a rate to be of any practical use.